We've already seen an example where we have initial and one or more equilibrium concentrations, and we want to calculate the equilibrium constant. But there will be other examples where we know the equilibrium constant, and we know at least one initial concentration, and we'll want to use those two things to find the equilibrium concentrations. When we want to find the equilibrium concentrations, we'll still find it useful in order to use the ICE tables that were introduced in the last example. The other thing that is new that we'll introduce is that any problem where the equilibrium constant is given to you, we'll find it useful to use x in an equation in the change row to help us determine where the equilibrium concentrations are for reactants and or products. Since we're using x in these equations, we'll find it useful occasionally to use the quadratic equation to solve for x. In this example, we have a reaction between nitrogen gas and oxygen gas to produce 2 moles of nitrogen monoxide. And the K sub C value at this temperature is 0.10. Now, in the problem, we're given the initial concentration of N2 and O2, and we're asked to find the equilibrium concentrations of the nitrogen gas, the oxygen gas, and the nitrogen monoxide gas. The first thing we'll want to do is prepare an ICE table. And we can continue by filling in the initial values that are given to us. We can then use our assumption about the amount of initial products that we have. Since it's not specified in the given problem, we can assume that the initial concentration of NO is 0 because the reaction has not started yet. The next thing we'll want to know is we'll want to determine how much the concentration of each reactant and product changes. Now, in this case, we know the initial values, but we do not have any equilibrium values to tell us how much either reactant or product is changing by. Since we don't know how much the change values are going to be, we'll use what we usually use whenever we have something that we don't know, and we'll use the value of x. In this case, we'll say that the nitrogen is changing or decreasing by x. Since the nitrogen and the oxygen have a 1-to-1 mole ratio, the oxygen will decrease by the same amount, or minus x. On the product side, the NO gas has a coefficient of 2, so that means that it'll change by twice as much as either the oxygen or the nitrogen. And since it's a product, it will have a positive change, so for the change row, we can say that the nitrogen monoxide has a change of plus 2x. Now that we know all of the initial and change values, we can use the initial and change for each reactant and product to calculate the equilibrium values. For the nitrogen gas, 0.20 minus x gives us an equilibrium concentration of 0.20 minus x. Since the oxygen has the same values for initial and change, we get the same value, 0.200 minus x, for the oxygen. In the case of nitrogen monoxide, we started with a 0, and then it increased by 2x, so at equilibrium, the nitrogen monoxide gas will have a concentration of 2x. Next, we'll want to use the equilibrium concentrations we just wrote down and substitute them into the equilibrium constant expression. We start by writing the equilibrium expression, and in this case, remember that the nitrogen monoxide has a coefficient of 2, so we'll square that concentration in the equilibrium expression. We also already know the value of the equilibrium constant, so we include that as well. Now we take each of these equilibrium concentrations and we place them into the equilibrium constant expression. Since in the denominator the 0.20 minus x is multiplied by 0.20 minus x, we can rewrite this as 0.20 minus x squared. Since both the top and the bottom of the denominator have squares, what we can do is we could take the square root of both sides of the equation to get rid of those squares. When we take the square of 0.10, we get 0.316, and when we take the square root of the other side, we just get 2x on the numerator and 0.200 minus x in the denominator. We can now multiply both sides by 0.200 minus x to get the 2x by itself on one side. This is what we get when we multiply the 0.316 times each of the factors inside the parentheses. Now we can add 0.316x to both sides in order to get the x terms on the right-hand side of the equation, and this is the equation that we get. We can now add these two x terms together, and once we do that, we can solve for x by dividing both sides by 2.316. And if we look back at the original problem, we see that we're going to be limited in our answer to two significant figures. And in our answer, we get a value of x of 0.027. However, that's not our final answer. Remember, what we are looking for is the actual equilibrium concentrations for the two reactants and the product. So now that we have this value of x, we'll substitute that value of x into each of those equilibrium values that we found earlier. So that's the last step, is to substitute the value of x into each of these equilibrium concentrations. The concentrations of nitrogen and oxygen will simply be 0.200 minus the value of x, which is 0.027, which gives us a concentration of 0.173 molar for both nitrogen and oxygen. So the concentration of nitrogen monoxide at equilibrium is equal to 2x, so 2 times 0.027 is 0.054 molar, and those are the three equilibrium concentrations. So in this problem, we were looking to use the equilibrium constant to find the equilibrium concentrations, and we were starting with initial concentrations of reactants. We followed these steps using our ICE table to find the value of x, and once we found the value of x, we plugged it into the equilibrium concentrations that had x in their expressions, and then we substituted the value for x to find what the equilibrium concentrations were. Now before we leave this example, I just want to remind you that there may be situations where we get to this step where we've plugged in our equilibrium concentrations and our value of k, and then we have to solve for x. Now in this case it worked out that we could simply take a square root to get rid of the x squared terms, but it's not always going to work that easily. In some situations you'll have an x squared term and an x term and then a numerical term without x, and in those situations you'll have to use a quadratic equation. And you could either use a quadratic equation solver on a smartphone or on your programmable calculators, or you could solve a quadratic equation longhand.